This is another short video lecture on helping you achieve the best possible grades you can for the final exam. We're going to look at some problems relating to an introduction to confidence intervals. As always for these videos, you'll see me using the Wolfram language. Remember, this is not about a computer language though. I'm using it to do my calculations and I'm using it to create the plots so that I can explain the solutions to you. What I do want you to use for the calculations, of course, is a spreadsheet, and a link to those spreadsheets will be in the description down below. So question number 1, write an informal definition for a point estimate. And the solution that I wrote here is a point estimate is a single value given as an estimate of a population parameter. So we're going to take a sample from a population, we're going to calculate that sample mean. That is a point estimate, and it is a single value that is what we think is a good estimate for the population mean. And so I've written some code just so that we can explore this answer a little bit. Now, you do not have to follow the code at all. This is code written by me, for me, so that I can explain the concepts to you. So what I'm doing in this first code cell is just to create a set of values. I'm just suggesting that my whole population consists of 50,000 subjects, and I'm just creating 50,000 values for a ratio type numerical variable, and I'm just taking that from a predetermined distribution. I'm assigning that to a computer variable that I call population, such that we can calculate the population mean. That's our parameter. So for my self-generated population, I came up with this population of values. I decided, how these values should be generated. And I find for my whole 50,000 subjects, for this ratio type continuous numerical variable, we find a population mean of 99.9427, as you can see there. I can also calculate the standard deviation. So this is another population parameter, and we see the population standard deviation is 15.007 right there. Now, what I'm going to do, I'm going to imagine that I'm a researcher, and I'm going to select from my population of 50,000 subjects, I'm going to select 100 subjects at complete random. And so that's what I do with this bit of code here. I randomly select 100 subjects from my population, and I can now calculate a sample mean. In other words, I'm calculating a point estimate. And there we can see my 100 random subjects, the sample mean for our continuous numerical variable or our ratio type numerical variable is 100.009. And so there we can see the true population mean, or that is a population parameter, is 99.9427, and our sample mean is 100.009. Very, very close to each other. A sample mean is an unbiased estimator of a population mean. Question number 2, write an informal definition of an unbiased estimator. So we say an estimator is unbiased if it produces parameter estimate values that are on average correct with respect to the population parameter. And that's just what we've seen here. A sample mean is an unbiased estimator of a population mean. I've just shown you one example here, and it turned out that the values were very close to each other. So let's use some code again. Again, don't follow the code unless you want to. Unless you want to learn how to use this computer language, which is the Wolfram language, you can just ignore the code. So what we're going to do here is imagine that we could select 100 subjects from our population of 50,000. I select my 100 subjects at random, and I calculate a mean for those 100 values. Now I've got a single mean. And imagine I can repeat this exercise. The next day I might get up and I select another 100 subjects at random from my population, and I calculate a mean. Now I have two means. Now imagine I can do this over and over and over again so that I have a bunch of sample means. And I would call that a distribution of sample means. So in the code here, I'm going to randomly select 100 people, calculate a mean, and I'm going to do this 2,000 times over. Very unrealistic, because you cannot do this in real life. You can only do your study once. Select your 100 people, your 100 subjects once. I'm here simulating as if I could do this 2,000 times over. And let's look at the mean of all my 2,000 means. And I can see that's now 99.8842. And I do remember that the true population mean, that population parameter was 99.9427, very close to each other. The sample mean is an unbiased estimator of the population mean. So let's just have a little look at a histogram of my distribution of sample means. And there we go. I've also added for you as a red dashed line there, the population mean. That's a true value, a population parameter. There we see, and we can see this histogram is centered around the population mean. So this is a sampling distribution of sample means, and we do know if one of the two assumptions are met. Number one is the variable itself must be normally distributed in the population, or I have a sample size of at least 30 subjects. If one of those two are met, I can invoke the central limit theorem, and that's exactly what we see here. We see a normal distribution to all the possible values that the sample mean can take. So do remember, on my horizontal axis here, I have sample means, and I simulated doing this 2,000 times such that I have 2,000 sample means, as if I did my study 2,000 times over, and we can see how it centers around the population mean, the true value. And so we can state there that the sample mean is described by the normal distribution, and remember, normal distribution is described by two parameters, depends on two parameters, the population mean and the population variance, and that's what we can see there. Do remember, though, that I can always take an x-bar value, in other words, a sample mean, and I can express it as a z value. I can standardize each possible x-bar value by subtracting the mean and dividing by the standard error. And remember, the standard error here is the population standard deviation divided by the square root of the sample size. And z is described by the standard normal distribution on a mean of 0 and a variance of 1. Great, right? An informal definition for a confidence interval. And I've written here, a confidence interval is an interval of values with a lower and an upper bound around the point estimate, which is expected to typically contain the parameter being estimated. So if I have a sample mean, I'm going to calculate a lower bound and an upper bound around that mean, and I have a certain confidence that within those values, within that interval, I will find the population parameter of interest. In other words, the population mean for our example. Question number 4. Explain C, the confidence coefficient, in the equation for the confidence interval around the sample mean x bar, where sigma is the population standard deviation and n is the sample size. So there's our equation. It's x bar plus or minus C times the standard error. So I want to know what that C is. Now, just be careful. Not all textbooks describe that C as a confidence coefficient, but in our course, that's what we call a confidence coefficient. And I just want you to understand what that C is, and we can see it right from this equation here. The confidence coefficient C is the units of standard error away from the mean. I'm taking C, it's a coefficient multiplied by a certain value. That value that I've highlighted there is the standard error. So C times the standard error is how many standard errors. If you take something like 3 times 4, that is 3 4s, which is 12. That was 3 units of 4. And here is C is how many standard errors do I want to be away from the mean. And I'm going to subtract that from the sample mean, and I'm going to add that to the sample mean. So let's just read our solution again. The confidence coefficient C is the units of standard error away from the mean that calculates the lower and upper bound of the confidence interval around the sample mean x bar. So let's just use a bit of visualization to understand this. Remember, any x bar value that I can possibly find, remember if I could do my study over and over again and I'm going to find a bunch of sample means x bar, I can standardize each of them by taking each one of them, subtracting it from it, the population mean, and dividing by the standard error. And that tells me how far each possible x bar value is on that horizontal axis away from the population mean in units of standard error, and that is z. So z represents the units of standard error that a value x bar is away from mu. So let's just visualize this. I can take any value x bar and I can transform it into a z value. I can standardize it. So any x bar that I can possibly find, how far is it away from mu? Well, I'm just expressing this on my horizontal axis in units of standard error. And now look, if we think about C, the confidence coefficient. If I want an alpha value, now I don't want to say too much now about an alpha value right now, that is for the next lecture, but if I click on these, you can see my little red zone move around. So at 0.05, what I actually am is right there, this little green line there, it is 1.96 standard errors away from the mean. And if I do that, look at my red zone from negative 1.96 to positive 1.96. That'll actually be 95% of the most probable values that Z can take. And remember, when I say Z here, that's just a transformation of X bar, the sample means. So think about this horizontal line as just units of standard error away from the population mean. And if I want to capture the 95% most probable values, I've got to be within 1.96 standard errors away from 0. That would capture this middle 95% most probable value. So let's look at question number 5. Calculate the confidence coefficient for the Z distribution for a confidence level of 90%, 95%, and 99%. So let's go back to this figure that we've just seen. A confidence level just means I want to capture an interval where I would find the most probable values, the 90% most probable values, the 95% most probable values, and the 99% most probable values. And this is what we have. Look at this red zone. If I click on this, look how big that red zone is. I'm capturing 99% of the most probable values that Z can possibly take if I do my study over and over again. And remember, Z is just a representation of X bar, the sample means, all the possible sample means, just expressed in how many standard errors they are away from the population mean. And you can see here, my little red zone. It's very improbable to find values outside of this red zone. This red zone represents 99%, the 99% most probable values, and that's my confidence level. I want a confidence level of 99%. In other words, I want to capture the 99% most probable values. And because this distribution is symmetric, of course, it's going to be the same on either side. If I want to be 95% confident, look how it jumps. There was 99. Look at the red zone. It becomes smaller. I'm now capturing the 95% most probable values. And here, smaller again. Now I'm capturing the 90% most probable values. Of all the possible values, if I were to do this over and over again by the central limit theorem, I'm going to get all these possible values. Some will occur more commonly than others. That's what I mean by probable. And now we can see if I am right here, I'm 95 or 90% confident. I'm just capturing the most probable 90% versus 99 out there. I'm capturing more. So I have used code here to calculate these values, and I'll show you just in a minute how you can use the spreadsheet. A link to that spreadsheet is available in the description down below. And so here are my confidence coefficients. For a 90% confidence level, I am capturing the 90% most probable values in the middle. That gives me a confidence coefficient of 1.64. I'm saying if I am 1.64 standard errors away from the mean, which is what these Z values are, I would capture 90% of the most probable values. So let's click on that one just to visualize what's going on here. That's the narrow one. This is the 90% of the most probable values. Remember, the whole area under the curve is 100% of all possible values. So right there, if I'm at 1.64, here I'm at 1.64 standard errors away from 0. And on this side, I'm also 1.64 away. It's just on the negative side. If I am 1.64 standard errors away from the mean, I will capture the 90% most probable values that Z can take, and hence my confidence coefficient for a 90% confidence level is 1.64. If I go to 95%, I get 1.96. So let's go there and look at this. I'm capturing 95% of the most common values, and look here. My bound has gone to around about it's difficult to be right on the spot there, but there, 1.96. If I am 1.96 standard errors above or below 0, I will capture 95% of the most probable values. So my confidence coefficient for a 95% confidence interval or 95% confidence level is 1.96, either above or below 0. And then finally, for a 99%, it'll be 2.57. So if I go to 99% here, look how far out I am now. I am 2.57 about standard errors away from 0. If I am that far away, I'm capturing the 99% most probable values. Great, let's go to the spreadsheet software and I'll show you how to do that. So here's our spreadsheet. Now, there are two tabs here at the bottom, two sheets. I want you to be on the Z distribution sheet. Now look at the top. We use the sheet if the population standard deviation is known. So there we go, the confidence coefficient. I just type in here my confidence level. If I want to be 90% confident, I find a confidence coefficient C of 1.644. I can also just type in, remember all the light gray zones are the ones you have to fill in a value. If I want 2 decimal places, it's just going to round 1.6448 to 2 decimal places, that's 1.64. So the confidence coefficient C for 90% confidence interval is 1.64. If I want a 95% confidence level, that's going to be 1.96. If I want a 99% confidence level, I get 2.58. Great, now that you have a good understanding of confidence levels and how they relate to confidence coefficients, let's go to question number 6. Researchers collect data for a ratio type numerical variable from 60 subjects and calculate a sample mean X bar of 343.3. They know the population standard deviation for this variable to be 33.7. Calculate a 95% confidence interval and write an interpretive view of the result. Now, what do I mean by interpretive view is not a true statistical explanation for what it is, but just how we normally interpret and normally write in a manuscript what we mean by the 95% confidence interval. So here's my solution. I'm just writing down what I know. I was told that my sample mean was 343.3. My population standard deviation was 33.7. I have 60 subjects in my sample. I know for a 95% confidence interval, I can go to that spreadsheet or I can use code, and I know that that is 1.96. If I'm 1.96 standard errors away from the mean, I'm capturing the 95% most probable values that X bar can take. And now here's my equation, X bar plus or minus C times sigma divided by square root of n. And I'm just using code here as my calculator. So I'm saying 343.3 minus 1.96 times the standard error and 343.3 plus 1.96 times my standard error. So I'm just plugging those values in, and let's see what those bounds are. It's 334.773 and 351.827. So we are going to say we are 95% confident that the population mean, that true value in the population, is between 334.8 and 351.8. 334.8 and 351.8. We are 95% confident that we will find the population mean between those two values. But remember where it came from. It came from this theoretical distribution, the standard normal distribution, and thinking about capturing the most probable values. And I'm using capture there as an English word as opposed to a statistical word in its definition. I'm just talking plain English here. So that's where we think in that interval we'll find the population mean, and we are 95% confident that that is so. Let's go to our online calculator. So I said I want to be 95% confident. Let's revisit the sample size. The sample size was indeed 60. Our sample mean was 343.3. Our population standard deviation, 33.7. And then we find our confidence coefficient, our lower bound, and our upper bound. So let's just put that in. We want 1 decimal place. And we see there, 334.8 to 351.8. The same values that I find here when I use the Wolfram language as my calculator. But please feel free to use the spreadsheet that I have provided. So let's look at question number 7. We're revisiting question number 6. Would the interval be wider or narrower if we used a 90% confidence interval? So let's go back to the theory. There's my 95% most probable values. Let's jump to 90. Can you see that got narrower? Let's go again. 95 wide, 90 narrower. I'm now only capturing the 90% most probable values. My C is smaller, and I'm taking C times the confidence coefficient. And if C is smaller, of course, I'm going to subtract and add a smaller value to X bar. And in fact, if we do that, which I've done for you here, let's do those two quickly. Get those two calculations. Remember, you can use the spreadsheet. Now I get 336 to 350. It's now between 336.2 and 350.4, and before it was between 338.4 and 351. It is now narrower because my confidence is now 90%. question number 8. Revisit question number 6 again. Write a statistical conclusion to the 95% confidence interval. So before I asked you for an interpretive result, now I want you to be more precise. What does it mean statistically to say a 95% confidence interval? And so let's read my solution here. In a great many repeat experiments of selecting 60 subjects from the population and calculating a sample mean with a 95% confidence intervals, which will be slightly different due to chance every time I do this, if I were to do this many times over, we will find that 95% of the confidence intervals would contain the population mean, and 5% of them will not. But very importantly, we can never know if our interval from our one study actually is one of the 95 that contains the population parameter, the population mean, or is one of the 5 that do not. We can never know that. So in normal English, we would just say we are 95% confident that the true population mean is between the lower and the upper bound, but in reality, that's not really what it means. Remember, what it means is if I were to do my study many times over, every time I'm going to find a slightly different x-bar, in other words, a slightly different lower and upper bound. If I were to do this an infinite number of times, in 95% of those cases, I will find it will contain the population mean, and in 5% it will not. That's what it means, choose a 95% confidence level, and so it is for the other percentages as well.